Good afternoon. I'm Spot On Weather meteorologist Matthew Euler. Today we're going to take a look, video number 3 in the training series, the summer video weather training series, video number 3, and we're going to talk about pressure systems, the cause of changeable weather. If you take a look at the image on the left-hand side, lots of sunshine, beautiful clear blue skies. That's an example of the weather you would typically see with high pressure systems. The image on the right is a visible satellite image of a March 2014 nor'easter, a special type of extratropical cyclone that moves up the East Coast, and that is associated with lower pressure. So we're going to get into the causes of the changeable weather, the pressure system, all the pressure systems in this video. All right, so first let's talk about something very important that's known as a pressure gradient force. Now, it's abbreviated by the letters PGF for pressure gradient force. And this is simply the change in the pressure over a certain distance. And you can have a pressure gradient force in both a horizontal direction as well as a vertical direction, right? The air, when we talk about high and low pressure systems, we talk about the horizontal change in pressure, we talk about pressure gradient force, we typically look at the surface pressure level. And we have high and low pressure systems. High pressure systems are usually indicated by a blue colored H, the low pressure systems by a red colored L. And air is going to always blow from higher towards lower pressure. There's pressure differences created between these high and low pressure systems. And whenever you have a pressure difference, that gets the wind flowing or the air moving in the horizontal around these surface pressure systems. And air always blows across lines of equal barometric pressure that are known as isobars. The wind blows at an angle across the isobars, and that's mainly due to the force of friction as the wind blows from higher towards lower pressure. On the right-hand image there, the bottom right, I'm showing a vertical pressure gradient. Now, we have a fairly significant vertical pressure gradient force. We have a larger heat difference between the surface and the upper levels of the atmosphere in the summertime. So you can actually get higher pressure at the surface and lower pressure aloft, just by the virtue of the fact that the air is more denser closest to sea level, and it gets less dense as you go up aloft, or the higher you go in the atmosphere. And this creates a pressure gradient force. Air tends to be directed from higher pressure at the surface towards lower pressure aloft. And whenever that happens, you have something that's known as hydrostatic equilibrium, and that's when your upward directed vertical pressure gradient force is balanced by the downward force of gravity. That we really don't need to get into that one, but I'm just showing you there's two different levels or dimensions at which there's pressure gradient force or changes in pressure. Over the horizontal, on the surface level at the ground between high and low pressure systems, and then also in the vertical. So now let's talk about the I'm going to move on along here. Now let's talk about the a couple main features here. Okay, the first thing we need to talk about, these dark lines on this particular chart. Okay, those are known as isobars, and iso means equal, bar referring to barometric pressure. So everywhere along one of these lines, it's the same pressure reading. Okay, so we have one dark line labeled 1008 millibars. The next line below that is labeled 1012 millibars. The line below that 1016 millibars, and so on, all the way up to 1024 millibars. So there's these lines of equal barometric pressure that are known as isobars that are typically found on the surface, right? Surface weather charts. Now, the difference in pressure between points C and D, that, let's say, is about 5 millibars, okay? I'm just measuring the difference in pressure along that red horizontal line between points C and D, along that red line, okay? At point C, the pressure is about 1,011 millibars. At point D, it's about 1,016. So we take the difference in pressure between those 2 points, 1,016 millibars, subtract 1,011 millibars from it, and we get 5 millibars, a pressure gradient or a change in pressure of 5 millibars. Now, I don't really have the distance calculated on here yet, but I will here in a minute. If you go down these black lines, follow down to the points A, labeled A and B, the difference in pressure between points A and B is 12 millibars, right? Because if I look at the pressure at point B, I'm at 1,016 millibars. And then if I look at the, following along here, and then the pressure at point A is 1,008 millibars, okay? Remember that every one of these lines represents a 4 millibar pressure change, okay? So I got about a 12 millibar pressure difference, between points A and B. And in this case, I have what's known as a steeper pressure gradient force. So the spacing of these black solid lines known as isobars, these lines of equal barometric pressure, the closer they are packed together, closer they're spaced together, the stronger the change in pressure over a shorter distance, and that gives me a steeper or a stronger pressure gradient force. If the black lines are spaced further apart, that gives me a weaker pressure gradient force. And as a result of the spacing of these lines, that equates to what kind of winds we feel here where we live on the ground. If I have a steeper pressure gradient force, I'm going to have a greater pressure change over a shorter distance, and as a result, the air is going to accelerate. And when it accelerates, it results in windier weather, windier conditions. Now, if my lines are much further apart, I have a weaker pressure gradient force or weaker pressure gradient, and my winds will not be as strong. So if you're ever around some major mid-latitude storms, especially in the wintertime, when you get a really strong, sharp temperature gradient, a really sharp pressure gradient, you can really get a lot of wind associated with cyclones in the wintertime especially. All right, so let's break down the differences between highs and low pressure systems, okay? This is a very important part of learning about pressure systems. For highs, these are also known as anticyclones, and they're basically a dome of higher pressure. So some key points about high pressure systems. Number one, the area around highs are surrounded by lower pressure. Secondly, in the northern hemisphere, the circulation around high pressure systems is clockwise or anticyclonic. Third, the wind flows outward and away from the high pressure center, right? Fourth, there's a weak horizontal pressure gradient near the center. So typically when you have high pressure systems move overhead or get relatively close to your area, you have a weak pressure gradient force, weak pressure gradient in the horizontal. And that means that the winds are going to be much less. So you'll have light to calm winds in a lot of cases when you're at the center of these high pressure systems. Fifth, the weaker calm winds, like I just mentioned, that kind of ties in with number 4, with that weaker horizontal pressure gradient. And then finally, they're labeled as a blue H on the surface weather charts. So if you ever watch the nightly weather on TV, the newscast, you may see a surface chart showing a blue H or a red L. Well, the blue H, it represents those surface high pressure systems or these anticyclones. Breaking high pressures down further, if we look in the horizontal, the air generally blows outward, away from the center of high pressure systems. It blows at an angle across these lines of equal barometric pressure, these isobars, and it's mainly due to the fact of friction. As wind blows outward away from the center is the high. It's going to blow over the ground. The ground is going to slow down that wind speed a little bit, or maybe the wind is blowing into buildings or trees or houses. That tends to result in friction. Friction as that wind blows across these surfaces, and that results in that air flowing, the wind blowing outward at an angle across the isobars from higher toward lower pressure. The image on the left shows in the vertical, high pressure is synonymous or similar to a hill or mountain in the atmosphere. Okay? So typically if I was to look at a vertical cross-section of a high pressure system, it's going to look like a big mound. Okay? These heights and the thickness levels increase. The heights increase, the atmosphere expands, and it looks like a hill or a mountain. Now, how do high pressure systems form? Well, the first thing we have is this upper level convergence, and that's right below the tropopause on this diagram. You'll notice how the black arrows are coming towards each other. This is when air comes together in the upper levels of the atmosphere, it's known as convergence, when air comes together. And as the air converges just below the tropopause in the upper atmosphere, as it meets, it's got to go somewhere, so it goes down. A lot of the air will go down, resulting in sinking air motion. And as the air hits the surface, it's got to go somewhere again, so it spreads outward or diverges along the Earth's surface. So you get low-level diverging winds. Okay? So you have increased mass in the upper portion of this air column, and that will eventually lead to downward sinking air motion, and it results in air pressing down, air sinking and pressing down on the Earth's surface, which is going to result in higher pressure. Remember, pressure is simply force per unit area. So the more the air sinks, the greater the sinking motion, the higher the pressure will be at the surface, the greater the force per unit area. This is exactly what you'd expect with high pressure here. Okay? You get clear skies, again, do that sinking air motion. As air sinks, it warms and dries, and it results in the absence of clouds. So on a really nice day where the sky is crystal clear blue, there's no clouds, there's a good chance you have high pressure overhead. What's the structure of highs look like? Okay, we're going to start off with something known as a warm core high at first. Now, warm core highs, when I say warm core, what I'm getting at is the highest temperatures are towards the center. All right, so warm core highs typically form over the subtropical and tropical regions. They're large areas of sinking warm and drier air. Higher heights above the surface high, or there's ridging aloft. What we call ridging aloft is when you have higher heights above that surface high. So with high pressure, remember, it's like a big mountain, so the heights are going to rise above that surface high. With a warm core high especially, when you're involving warmer temperatures, the atmosphere is going to be much more expansive. The vertical axis will stack back to the warm air at the equator. So these are some facts about warm core highs. So here's a diagram to illustrate an example of a warm core high. You get this upper level convergence again where the air streams come together. Okay? As they meet each other, they have to go somewhere, so that results in that sinking air motion downward. And then as that sinking air motion hits the Earth's surface, you get that low-level diverging air where it's spreading apart. And notice there is that little hill below the blue H here. You got the high pressure at the surface. You've got this expanding atmosphere directly above the high, especially since there's warmest temperatures at the center. And you see these almost like hill shapes at every level above that blue H. And that shows ridging aloft, or higher heights generated above that warm core high. And by the way, when the upper level converging air streams are greater than the lower level diverging air streams, you get more mass accumulated in the upper levels of the atmosphere. You get greater sinking motion, and this is known as the damper effect. Here are some of the other interesting facts about warm core highs. We talk about, I mentioned that they form over tropical and subtropical regions. When I'm talking about subtropical regions, I'm generally talking about the latitude of 30 degrees. It can be 30 degrees north over the ocean or 30 degrees south over the ocean, over the subtropical regions at 30 degrees latitude. The warm core highs play a big factor in our weather during the summer, especially in the East Coast, because you have these huge expansive, they're called subtropical high pressure systems or anticyclones. They're warm core highs, and they sit over, for example, if we use the US as an example, the Atlantic high pressure system, subtropical warm core high, sits over those waters and actually expands northward in summer. And what we get is a clockwise flow of air around these highs over the ocean, and that results in warm, humid weather in the summertime across the eastern US. These are large, persistent pressure systems. These are types of systems that don't just come and go. They pretty much remain in place throughout the year, but they are stronger. Subtropical highs are stronger in the summer hemisphere, and they expand poleward in the summer hemisphere as well. Now, they also remain approximately the same location year round, and again, there's a shift slightly north and south with the seasons. And I put in parentheses here, these high pressure systems or warm core highs generally follow the sun between summer and winter seasons. So, for example, in the summer season in the northern hemisphere, the sun moves further north up to the 23.5 degree north latitude line, the Tropic of Cancer. The subtropical high pressure or warm core highs, high pressure systems, also known as the Bermuda High, expand northward. They ridge up northward to higher latitudes in the summer months. And then when we get towards winter, the sun makes its path toward the southern hemisphere, the most direct rays of the sun. And as a result, the subtropical or warm core high shifts further south closer to the equator and is much weaker in the winter season. So they have a huge impact on our weather and what we actually experience. Here's some examples of the warm core highs over the subtropical waters of the Atlantic, the Pacific, and the Indian Ocean. So just keep in mind, these high pressure systems generally sit at about 30 degrees latitude in both the northern and southern hemispheres. And the front side of high pressure systems tend to have sinking air motion, or the east side of high pressure systems are more stable, resulting in sinking air motions and a lot of clear skies and dry weather. So a lot of these high pressure systems are responsible for producing the deserts of the world. For example, if we were to look at the deserts of Africa, okay, we look at the Sahara Desert, those are mainly caused by these subtropical warm core highs just sitting in the same position year round, and those locations are generally located on the front or the east side of these high pressure systems, which is the stable side of the high, and that creates world deserts around 30 degrees latitude. Now, on the other hand, we have something that's called a cold core high. Just like we had a warm core high, now we have something known as a cold core high. So when I say cold core, what I'm getting at is the coldest temperatures are towards the center of this pressure system. And just like we had with the warm core high, we have upper level converging air streams. So the red air, the pinkish reddish arrows are coming together just below the tropopause. As they meet, the air has to go somewhere, so it sinks and goes downward. Once that sinking air hits the surface, the air diverges or spreads out, and that results in that blue H on the surface, a high pressure system. But look at the difference here between the warm core and the cold core high. With the cold core high, we have something known as cold air advection, or the transport of colder air above these high pressure systems. You see up at 30,000 feet, and 18,000 feet, we now have a almost looks like a dip in that line there, showing that's the upper level trough at 18 and 30,000 feet. You have a little bit of a ridging at 700 millibars or 10,000 feet, and then you have a ridge extending downward to 850 millibars or 5,000 feet. There's intense surface cooling associated with these cold core highs. They generally form over land, and again, the ridge weakens with height. It actually becomes an upper level trough at the higher levels of the atmosphere. That colder air aloft will result in a much denser atmosphere, and at 30 and 18,000 feet, the air is actually sinking because that colder air comes in and causes the upper level heights to actually fall. So there is a big difference between the warm core high and the cold core high. Some facts about cold core highs is usually it's associated with a dome. I call it a bubble. A bubble of cold air, continental polar air typically from Canada, will break off, come southeast, and this is really a big factor in causing much colder temperatures in the wintertime, anywhere from the northern plains all the way down to the southeastern U.S. This cold core high will become larger in wintertime because the land masses are much colder, and that's what makes them stronger in the wintertime over the land masses. They're maintained by that upper level converging airstreams or convergence in the upper atmosphere aloft, and they're also maintained by being over a much colder surface, a land surface. This cold dome of high pressure is shallow, and it weakens with height, as I indicated here. You see how we have like a hill, looks like a hill shape at 5,000 feet and at 10,000 feet with that ridge, and then above that, higher up in the atmosphere, above the cold core high, you actually have a dip, upper level trough over the top of this. Okay, so let's take a look at some locations of the cold core highs around the globe. All right, and again, these are more prominent and they're much stronger in wintertime when you have a colder landmass, especially at the higher latitudes. There's limited sunshine, longer nights, usually a snowpack, snow-covered ground, which relates or results in much colder surface temperatures, and this results in a much stronger cold core high pressure system. So look at, you're over Russia with a cold core high, especially in the winter. They call it the Siberian high, and then also over the United States. It comes down from Canada quite a bit. A piece of cold air will break off and be transported southeastward on the jet stream. The jet stream will push that cold air southeast, push this high pressure southeast, and it'll be much colder conditions. Now notice the absence in the southern hemisphere of these cold core highs, because what we're looking at is, in order for the cold core high to thrive, we need a cold landmass. Well, there is less landmass. There's only 40% landmass in the southern hemisphere compared to 60% landmass in the northern hemisphere. So we have more water. We have more water and less land masses in the southern hemisphere, and therefore we have an absence of these cold core highs. Now let's talk about another type of high pressure system. This is known as the transitory, I call it transitory, or baroclinic highs. Now these are caused by strong upper level winds. The jet stream, it moves over the cold core high, it breaks off a piece of the coldest air, sends a chunk of cold air into the lower 48, and the outer portion of the high begins to move. The jet stream pushes this baroclinic or transitory high southeast, and they tend to move towards the southeast, and they're responsible for the cold weather in the U.S. of wintertime. Warm and cold highs usually associated with good weather. They're both usually associated with good weather because of that sinking air motion. When air sinks, it dries out. So you get high pressure in the wintertime, or if you get high pressure, a warm core high pressure system, either way you're going to get clear skies and very nice weather because of that upper level convergence of sinking air. But these baroclinic transitory highs, they break off from the cold core high in Canada, and they send much colder air southeastward. And here's an example of a map you might see in the wintertime. You get the red arrow represents your polar front jet stream, and you get a strong cold core high positioned over northern Canada. And remember, the strength of that is dependent on a colder landmass beneath it. That red arrow represents a polar front jet. A piece of that cold air breaks off of the main high in Canada and it will follow this path, the red arrow path, the polar front jet stream path. Baroclinic systems involve temperature changes. This transitory or baroclinic high is going to get steered by the upper level jet stream winds and basically follow the path, the core of that jet axis. Okay, so here's an example of a transitory high. This happened on January 24th of 2003. This is a surface weather chart. The blue lettering there, that blue H, situated right near St. Louis, Missouri. The arrows, the gray arrows, representing how the air again flows outward and away from the center of high pressure systems in the northern hemisphere. Clockwise in the northern hemisphere flow around highs and outward away from the center. The temperatures on some of these station plots, the temperatures are the upper left value on these station plots. So upper left-hand value, we got some negative numbers. Now this is in degrees Fahrenheit. I am looking at a surface chart. So this is a case of where one of those strong cold shots came down from Canada. The high pressure system, or this transitory high, followed the path of the jet stream, brought much colder conditions into the Midwest, even to the deep south in this case, all the way to the East Coast. And so this happens quite frequently in the wintertime. Okay, so that wraps up our talk on high pressure systems. Now we're going to move into low pressure systems. And another name for these are cyclones. So some facts about low pressure systems or cyclones. Number one, they're areas of lower pressure. So if you were at home looking at your barometric pressure, your barometer, if you have one hanging up somewhere, and you notice your pressure is lowering over time, there's a good chance you have lower pressure moving in. Generally in the northern hemisphere, these general circulation around lows or cyclones is counterclockwise. If you simply look at the hands of a clock and you notice normally how the hands of the clock move, they generally move in a clockwise manner. When it's counterclockwise, just go against the hands of the clock. Think of the opposite direction, as if time were going backward on a clock dial. That's a counterclockwise circulation in the northern hemisphere. Winds are going to spiral inward toward the low center. Strong horizontal pressure gradients are going to occur near the center. And the reason you have stronger horizontal pressure gradient forces is because the air is just rushing in from the surrounding high pressure, and it's causing a greater wind. Generally strong surface winds near the center of low pressure systems, and this is going to be labeled as a red L on the surface weather charts. So for low pressure systems, we have a little bit of a difference as compared to highs. First of all, the low pressure systems are similar to a valley or a depression on Earth's surface. So you notice how there's a dip on that figure there on the left, and I have my red L, my low pressure, in the deepest part of that, right? The image on the right shows in the horizontal. Air circulates inward and blows towards the center. Right? So see how these orange arrows are all converging or coming together right at the center of that lowest pressure system right there, the lowest point, the lowest barometric pressure associated with the low center. Notice the aqua looking boxes and the values. Those are your isobars, those lines of equal pressure, and notice how they get lower and lower the closer you get to the low pressure center. So if I look at the formation of a low, we're going to have an opposite case here. This is known as the chimney effect. Okay, so now with the low pressure system formation, I got winds in the low levels of the atmosphere on the surface converging together. They're blowing together. And as they blow inward towards each other, they have to go somewhere. So the air rises in the vertical. All right, and once the air rises to a certain height in the atmosphere, upper level divergence occurs where the airstreams spread apart. That's known as upper level divergence. So if you have the removal of mass aloft in the upper portion of the column, that's going to result in the air converging, especially if you have faster diverging air over the top, just beneath the tropopause there. If the air is spreading out quicker in the upper atmosphere, you're losing a lot more mass. That decreased mass in that air column equates to lower pressure at all levels. It's known as the chimney effect. The faster the air is evacuated at the top of the air column, the faster the air converges at the surface, the faster the air accelerates in the vertical. This is the type of weather you would get with a low pressure situation. Cloudy skies with rain or snow falling to the ground is quite typical because you get a large amount of rising air motion. When air rises, it cools, it condenses, it changes from a water vapor to a liquid, and then that eventually forms raindrops, or what we call hydrometeors, snowflakes, and ice crystals and raindrops. Eventually, those are going to fall to the ground once they overcome the force of gravity. So again, low pressure centers, think stormier weather. Now, what do the structures of lows look like? So let's take a look at the warm core low first. With the warm core low, again, when I say warm core, I mean that the temperatures are increasing or getting higher towards the center. So with warm core, there's two types that can happen. There could be a thermal, or what's known as a heat low, and this typically happens over the valleys, the heated valleys of Southern California, especially in the summertime when the sun's radiation is much more direct. Or you can get a, with that warm core or heat low, they generally tend to remain stationary. I should mention that. The other type of low I was going to mention are tropical systems. That's another type of warm core low. So the hurricanes over the water, those are warm core lows, where the warmest temperatures are towards the center of the pressure system. Now, these warm core lows are not associated with fronts. They're generally associated with fair weather, with the exception of the tropical systems. Usually you lack divergence aloft, especially when we talk about more of the warm core heat low, which is over land, overheated land. It's more shallow, higher heights aloft, and the warm core lows over, especially over land, are formed by intense surface heating, where the air density will decrease or drop enough for a low to deepen or get stronger. And it's common in the desert regions of the southwest U.S. A lot of times in the July and August time period, you'll see a thermal heat trough set up over the central, the valleys of California, Southern California. So let's take a look in the vertical what a warm core low looks like. All right, so because there's intense surface heating, the air is much lighter and it wants to rise in the vertical. Okay, so as the air rises in the vertical, you have more air that comes in and converges the low levels of the atmosphere at the surface. And as the air rises with a heat low, especially over land, and even with tropical systems, you have a high pressure or anticyclone or a ridge aloft. So you see how there's the bending, the troughing at 850 millibars, 5,000 feet, and then also a bending of that line at 700 millibars, 10,000 feet. And then you notice the change at 18 and 30,000 feet, how now you have a ridge aloft, or where it looks like a big hill or a mountain again. That warmer air in the air column actually causes the air to expand, those heights to increase. Upper level heights are going to rise, especially above 18,000 feet. And again, it's going to form over water or land. It's going to weaken with height, the low pressure itself. Now, with a hurricane or tropical system, it's going to develop mainly from the warmth of the ocean water below. Those warm tropical waters act to create these warm core lows, and that's what happens there. Now let's take a look. Over land, these systems form over deserts. Okay, so if I look at the deserts around the world, you generally have dry weather. A lot of times, it's so dry in these areas that even though the air is rising over the deserts, it doesn't really result in any clouds or precipitation because the air is so dry. The whole column of air is so dry. So you look at Australia, the outback, where it's a major desert area. You look at Sahara area, Sahara Desert, the Sonora Desert over in Mexico, and then also look at over water. Look where the low pressure systems are over water, and those are associated with the tropical systems that could develop. But you notice how far south in latitude those are in the northern hemisphere? South of 30 degrees, basically between 0 and 30 degrees latitude, you get these warm core lows that form over the warm, moist tropical waters. Cold core lows, on the other hand, are much deeper systems, and they are going to deepen with height. They can appear as a low or a trough aloft, and they usually have upper level support in the form of a jet stream. There's upward or rising vertical air motion throughout the entire air column, and the cold core lows are associated with poor weather. You get these cold core lows quite frequently um, when they get cut off from the main jet stream. They can actually get cut off or removed from the main jet stream, and they can form what's known as cutoff lows. So let's take a look here at what happens with cold core lows. So now look at how you have a dip in the line all the way from 5,000 feet up to 30,000 feet, 850 millibars up to 300 millibars with a cold core low. The upper level divergence, or the spreading out of the air below the tropopause, is still there. You still got the air coming in and meeting and colliding and converging at the low levels. The air is still rising up to the air column. You get that rising upper vertical motion indicated by that vertical arrow. But the upper level divergence is happening quicker than a low level convergence, and you get this decrease in the overall upper level heights. So a little bit different. With cold core lows, there also could be semi-permanent lows. We have two in the northern hemisphere that we're most interested in. That would be the Icelandic low as well as the Aleutian low. They're persistent and they remain in the same location year-round. Again, the Icelandic low and the Aleutian low. Let me show you where the Aleutian and Icelandic lows set up. Right there. Okay, so the Aleutian low sets up in the Gulf of Alaska. Icelandic low, we call it Icelandic for a reason because it's close to Iceland. It's actually located between Greenland and Iceland. The regular mid-latitude cyclones actually over the oceans generally tend to migrate or move towards these semi-permanent lows. So we call them the low pressure graveyards because these actual mid-latitude baroclinic low pressure systems, or the low pressures we're used to getting with associated with storms where we live in the United States, these low pressure systems generally move towards the Aleutian and the Icelandic low, semi-permanent areas. Now, what about transitory baroclinic lows? These are a little bit of a different type of animal we're dealing with here. They're driven by upper level jet stream, typically the polar front jet stream, and are usually associated with fronts and air mass changes. When I mention the words baroclinic, when I mention that word, that generally means that there's some type of air mass change, there's some type of frontal system, and it's being supported aloft by an upper level trough or all the way up to the jet stream level. So again, this red arrow indicates my polar front jet stream. We have an upper level trough over the eastern U.S., dipping all the way down to the Gulf Coast states. I'm going to play this again for you. Notice the baroclinic, or this transitory low, is pushed along by the upper level jet stream winds, just like that transitory baroclinic high was. Okay, so you see the motion, the general path of this low pressure system. The baroclinic transitory low follows the overall jet axis, and that's generally how it's going to be steered. Here's an example of a surface chart of a transitory or a baroclinic low. We have a couple here on this chart. The one on the bottom right is at about 1,001 millibar central pressure. The one on the upper left is at 990, it's stronger, more intense at the 990 millibars, the upper left low pressure system. Generally, the wind barbs are indicating that counterclockwise wind circulation around low pressure systems in the northern hemisphere. Generally, this actual chart was taken on it's going to be March 17th of 2003. So you can kind of see how the winds are spinning inward. The arrows are showing the direction the winds are blowing inward towards the center of low pressure systems. I don't have a front drawn on here, but this is associated with actual frontal boundaries, warm and cold fronts respectively. All right. So in summary, this is what we have. We have, with high pressure systems, we have something that's known as a damper effect. It's where you have upper level convergence or upper level converging airstreams meet below the tropopause. As they meet, they then have to go somewhere, so that results in downward sinking air motion in the atmosphere. And as they meet the surface, once these winds come down, blow vertically down towards the surface, they generally spread out horizontally And high pressure systems are created, the sinking air is pushing more force per unit area, and that's what's causing high pressure. The right-hand image is the opposite. We have what's known as the chimney effect, and we have low-level converging air streams coming together. As those air streams come together, they have to go somewhere, so they decide, hey, I'm going to go up in the atmosphere. Rising air motion in the atmosphere usually results in stormy weather, clouds, and precipitation. Upper-level divergence over the top, air moving, spreading apart, removes that mass, and you get these formation of low pressure systems. So high pressure associated with nice fair weather, low pressure with stormy weather. And then here's another little summary, and this is to end it on pressure systems, our video training series 3 on pressure systems. Generally shows you we talked about a warm core high, a cold core high, a cold core low, and a warm core low. If you look at the image on the left, the warm core high, notice how you get these ridges or these upper level heights that are rising above the warm core high. Warm core meaning the warmest temperatures towards the center. The air is much lighter at the center of a warmer system, and therefore the heights rise in the form of an upper level ridge. With a cold core low, notice with the cold core low, you get a upper level low above it, and you get a bending down of these height lines, or the higher heights tend to dip and get lower at every respective level here. That's known as upper level trough. And then with a cold core high, generally form over land masses. You get ridging in the lower levels of the atmosphere up to about 700 millibars, but then you get an upper level trough that's situated aloft over the cold core highs because the air is cold, it's dense, it's trying to sink in the upper levels of the atmosphere, resulting in the upper level troughs. And then finally, the warm core low on the right generally shows ridging aloft over it, and then the bending down of your thicknesses, your upper level heights decrease closer to the surface with a warm core low. All right, that wraps things up for Pressure Systems Video Training 3. I hope you enjoyed this video. I really do. We had a really good session today talking about pressure systems, causes of changeable weather. We talked about the difference between high and low pressure systems. We talked about pressure gradient force, which gets things blowing from higher towards lower pressure. Pressure gradient force, or a change in pressure, is both in the horizontal as well as the vertical, as depicted by these diagrams, one on the left, surface high and low pressure systems in the horizontal, the one on the right in the vertical, showing that you have higher pressure at the surface because the air is more dense, lower pressure aloft. We talked about isobars, lines of equal barometric pressure, and then we talked about the spacing in the isobars. When the spacing of isobars is closer together, or there's a greater pressure difference over a specific distance, the tighter the packing of the isobars, the windier the weather we experience at the surface. The farther apart the isobars, the lighter the winds. Then we talked about a breakdown of some facts about highs or anticyclones. These are domes of high pressure, and the circulation in the northern hemisphere around away from high pressure systems, outward and away from high to low pressure. And all the time, remember, on the surface, the winds are going to blow at an angle across these lines of equal pressure, the isobars, due to the force of friction. We talked about in the vertical, the damper effect, how you have upper level converging air, sinking air motion, and then lower level diverging air. That increased mass in the upper levels of the atmosphere results in a sinking air motion. And this is the typical weather with high pressure. We talked about warm core highs, and then we also went into general locations. Cold core highs, same, and where they typically form, transitory or periclinic highs, very common in the wintertime, and then low pressure systems. All right, that wraps things up. It's Spot On Weather. Thank you again for watching our video training series. We hope you enjoyed it. I wish everybody a happy, safe evening wherever you are. Take care, and God bless. Spot On Weather. If we're not spot on, we're not doing it right. Until the next training video, take care, everybody.